So for those at home, this is question 10 from paper 1, so you probably almost certainly can't see that. But it's question 10 from paper 1 in the brown paper envelopes. Yeah, so they've done a bit of sign change, and they found that the one value was less than 0, negative, one value was positive. So yeah, we would normally say that's evidence that there's a root between A and B. So what could possibly be true, which would mean that wasn't the case? What's the word that we, or the phrase that we could use? What do you reckon, Lily? It wouldn't be an inflection. It's a function that, it could potentially be a function that isn't continuous. So for example, the classic case is 1 over x. So if I asked when is that equal to 0 and tried this value here, then I get a negative answer, and this value here, positive answer. But there's no crossing point, there's no root in between those two values because it's not continuous. So the answer here is, it's not necessarily true because the function might not be continuous. And we're often, in questions with sign change, we're actually given a sketch of the graph to show that it is continuous. Because once you've seen that, then you can say, yes, it is continuous. In this case, we're not. We're not given the function. So we are then, in part B, shown a student's attempt at using Newton-Raphson. So Grace, Newton-Raphson is just an alternative way of finding roots. It uses an iterative technique, and the formula is on the formula sheet. It involves differentiating the function. So you make your first guess, like we do with iteration, and you plug it, you use the first guess there, you plug it into the function there, and then you differentiate it and plug it into the differential there. So this student is trying to solve this, so they correctly rearrange it because it needs to be equal to 0. So they correctly rearrange it as that equals 0. They correctly differentiate it. They're told to use 5 as a first approximation, so they do that correctly. They say, right, okay, the next value of x, x1, is equal to the first value of x minus 5 substituted into that over 5 substituted into that. That formula on the formula sheet, so don't need to remember it. So, any idea, Charlie, about one of the two mistakes? Anyone else want to suggest what's happened here that could result in it? It's quite subtle in both cases. They've used a rounded value, yeah. So what we would have done is we would have done 5 equals, and we would have used answer then, wouldn't we? So we would have put answer minus 2 answer cubed plus 9 answer minus 25 over 6 answer squared plus 9, and that would have given us the same value, but we would have then pressed equals again, which would have used that value correctly. So yeah, they've used a rounded value, and the other one is subtle. Normally with these sorts of questions we're told to do it so many times, but with this one we're not. So he or she has done it twice, and then has said, so the answer is 2.613 to 3 decimal places. Well, we don't know that. We can't say that until we get 2 successive answers that give you the same answer to a particular level of accuracy. So they are incorrect in saying that that is the root. They've stopped too early. They've stopped too early. And what I'm hoping you will do, but not now, is maybe look to finish that question off. So that's hopefully another one we can chalk off from that first paper. It was on the original list of questions I said don't leave, but hopefully you will now be able to have a go at finishing that one off. I mean, it's pretty straightforward because you've got pretty much the correct way of doing it there with just those two errors. I am aware that we've never done a great deal of practice, but at the moment we're just going bang, 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 bang through stuff with very, very little practice. And I'm aware that's an issue. So it may be that your first priority at the start of the Easter holidays. Have I mentioned how important Easter holidays are? I may just have mentioned it. It may be that you look to do some practice of the stuff we've done recently, and Maths Genie, very good for basic practice. So some good stuff on iteration, some good stuff on Newton-Raphson, some good stuff on trapezium roll. Maths Genie, if you remember, is always good for straightforward basic practice. All right. The other resources I've given you in the past papers are less straightforward, but this is the sort of practice that in an ideal world we'd do in class. We'd spend an hour doing Newton-Raphson practice. Unfortunately, we can't afford that. Interestingly, parametric integration we didn't do, and not mentioned in the syllabus. But there is one example in the textbook on it. So I emailed the exam board and said, look, is it or isn't it? You don't mention the syllabus, there's one example in your textbook. So when I get a response, it may be that we have to do a lesson on that after Easter. I'll make sure that we cover that. Okay, so we're going to move on. I want to get through as much as I can before Easter while I'm in front of you. So I reckon we can get through vectors in 2 lessons, and that means next week we can move on to statistics, which I was going to do after Easter, but if we can knock off one of the 2 big topics we've got left, that means we can probably finish within a week of the Easter holidays after Easter. So that's the plan. 2 lessons on vectors, a week on statistics, mechanics videos over Easter, a week on statistics after Easter, then we're done, and then it's full-on revision, which hopefully will be really, really productive. So we're going to talk about 3D vectors today. Which incidentally, Maths Genie has a really nice set of questions, basic practice questions, which it may be worth you looking at once we've done it. Okay, I've got a question for you which may not be immediately, may not seem immediately obvious why it's relevant, but some of you whom I taught may remember me talking about going into business selling sticks, and when I want to post my sticks I have to put them in boxes. So here's a box. Let's say this is a small box. What's the longest stick I can fit in that box? Okay, so that's your first question. What's the longest stick I can fit in that box? Your first question is, well, where would that be? Where would that length be? But then I'm interested to know what's the longest stick I can fit in that box. Now, of course, there's a short way and a long way of doing this. And I'm wondering whether anyone knows the short way. The long way is to say, right, well, firstly, the longest dimension is sort of from here to here, although I could draw that in several different places. We call it the internal diagonal. And so the long way is to work out the base diagonal by doing the square root of 6 squared plus 4 squared, because it's the hypotenuse, and then using that length in that right angle triangle. So you've got your answer to that squared. So you've got the square root of that, gives you that diagonal there, and then you do that squared added to that squared, square rooted. That's the long way, but you may remember that actually there's a glorious shortcut, because the square root squared just gives you that. So actually the internal diagonal is just the square root of the 3 dimensions squared and added. Square root, not cube root. Don't think it's 3 dimensions so I need to cube root. No, it's just the square root. So that's the internal diagonal length. Square root of this dimension squared added to this dimension squared added to this dimension squared, and of course that could be done in any order we want. Why have I started with that question? Well, before we talk about 3D vectors, we need to talk about 3D coordinates. So normally coordinates are used to position us on a flat plane, and we do it by saying, right, we go this far along and this far up or down. So in order to move into 3 dimensions, we need another axis. So this room, for example, is 3-dimensional. If I wanted to be able to locate any position in this room, I need another axis. And what we do is we lay our XY axes flat. And we have a third axis which comes up at right angles into 3D space. And we call that our Z axis. And we describe positions in 3D space, surprise, surprise, with 3 numbers in a bracket. Where this is how far in the X direction, this is how far in the Y direction, and this is how far in the Z direction. So if we imagine that my room is like that, so this is the front edge, and that is the x-axis, and this is the z-axis, then the coordinate 6, 4, 3 is 6 meters along here, if we're dealing with meters, and then 4 meters along here, and then 3 meters up, so it's about here. Okay, so that's the location of this point. Now, what if I want to know how far away this point was from the origin? This is the first skill we need to learn. So if I want to know how far that point, which is, it's really hard to draw, isn't it? But say it's up here somewhere. How far is that from the origin? Well, can you see how that's the same as the question we've just solved with the box? It's the internal diagonal again, isn't it? So the distance from the origin of that point is just that. So if I want to know how far away from the origin that point is, it's the same as the internal diagonal question. So that's the first skill that we need to have up our sleeves. You might still be thinking, why has he got 3D vectors as his title and we're talking about 3D coordinates? Patience. I'm not going to demonstrate where this point is, because it would require me digging a hole in the floor. But let's say now we want to know the distance between these 2 points. So we don't want to know about how far they are from the origin. We could do that. This would be 1 squared plus 2 squared plus 4 squared, because it doesn't matter whether it's positive or negative. When you square it, you'll get 16 square rooted, and that's 2 squared plus 5 squared plus 1 squared square rooted. My question now is, how far apart are they? So what's the distance between those 2 points? It's the same problem. It's the same problem, because all I need to think about is, if I make this my origin, how far do I go to get to here? So if I think about the difference, the change, I'm actually going along 1 in the x direction, up 3 in the y direction, and up 3 in the z direction. -4 to -1, that's coming up 3. So the distance between those 2 points is that. Ooh.
Thank you.
So page 339, question 4, just very quickly, I promise you we are going to talk about vectors. No, sorry, page 339, question 4 is not, sorry, page 338, question 4. Page 338, question 4. Just see if you can answer that. So that's sort of a question that uses that fact. So page 338, question 4. So rather than getting caught up with algebra relating to k, I'm just going to call, so I've got from 7 to from -1, 2 to k 0, 4, the gap there is something which is actually 7 minus k or k minus 7, I'm just going to call it a, and from -1 to 0 that's going up 1. So I know that a squared plus 1 squared plus 2 squared, square rooted, must be 3. So that means that that is 9. And so a squared is going to take away 5, 4. So a is 2. So that means there's a difference of 2 between 7 and that value there. So it could be 5, it could be 9. There we go. So 3D coordinates describe position in 3D space. Right. So what about 3D vectors? Well, let's consider a point in 3D space. I'm going to make it positive, actually, sorry. So here are my axes. So along 2, up 3, up 5, so I don't know, it's up here somewhere. Let's call it point A. So my question is, how do I get to A from the origin? That journey there, well, we can describe that journey using a 3D vector. To get from 0 to A, I go along 2, up 3, sorry, back across 3, and up 5. So a 3D vector is very similar to a 3D coordinate with one very obvious difference. The rotation through 90 degrees. But that's it. That's it. And this is a particular sort of vector. This is a position vector which describes a fixed place in space. It describes how you get from the origin to a point. So it describes a point in relation to the origin. We're going to look at some position vector questions, and then there's a different sort of vector. And you may remember when we did vectors in 2 dimensions, we had a different way of writing it. A way of writing it that used I and j. So this vector is 2 i's, where I is a movement of 1 unit in the x direction, and 3 j's, which is a movement of 1 unit in the y direction. So we need another letter, which we call k. So I is a vector with length of 1 in the x direction, j is a vector with length 1 in the y direction, and k is a vector of length 1 in the z direction. They are called unit vectors, and this is unit vector form. You may remember I'm not a huge fan of this. I like this. So here's a sort of very straightforward position vector question. Now, you know, it would be nice if we were allowed to get up and wander around the exam room to get a feel for where these vectors were, these 3D coordinates were, in the way I just did a moment ago. Not such a good idea. And it's really hard to visualise points. So I'll tell you what I always do in questions like this, when there are points, I make no attempt whatsoever to get them in the right place. I just say, right, they've called the points A and B, so I'm going to go, that's A, and that's B. And these are points, and we're asked about position vectors, which is their position relative to the origin. So I'm going to put O in as well. So the first part of the question is saying, what's the position vector of A and B? So what it means is, what's that journey there, which we write like this. And the arrow is important, doesn't it? It changes the numbers if I change the direction of the arrow. And you know, although I love writing it in this form, unfortunately they want me to give it in that form. So hopefully that first bit is just easy. Remember, it's just twisting it. I'm interested to then see how you think you could describe that journey. That's what the second part of the question wants us to do. Part A hopefully is straightforward. I'm interested to see whether you can work out how part B goes. If you chose to write 0i, perfectly okay. So the thing I'm asking you to puzzle over is how you can get from A to B. Any suggestion? Any suggestion? Well, it's just like we had before with the distance between two coordinates. We're just asking, what's the jump? What's the difference? So to get from here to here, in the x direction, we've gone backwards 1. In the y direction, we've actually gone down 8 from 5 to -3. And from -2 to 7, we've actually gone up 9. So that journey there is just the difference. And the arrow is important because we would have got 1, 8 minus 9 had we been asked what's the vector B to A. The other way of thinking about this, which we did at GCSE, was to say, how do I get from A to B on roads that I know? Well, I can go down here and up here. Down here would be -1, -5, +2. And then up there is 0, -3, 7. So my x number is -1 plus 0. my y value is -5, -3, and my z value is +2, +7. So there's two ways to think of it. You can either look at the jump, or you can say, right, it's backwards along there and forwards along there. You get the same answer, whichever way you do it. So can I get you to work out the length of AB, which is just the same as with a coordinate. It's the Pythagoras thing with 3 values. And just a reminder about that notation, which we meet in 2 places, don't we? It means modulus, but in this case it means the magnitude, the length. So it's just the square root of that squared plus that squared plus that squared. And unless it simplifies beautifully, leave it in surf form. I mean, the fact it's -1 and not +1 and -8 and not +8 makes no difference to the answer, does it? So this vector here has a length of, what's that? That would be just over 12, won't it? Just over 12. This is a popular question. Describe a unit vector in the same direction as AB. Well, we've already met unit vectors here. These are special unit vectors, but the actual definition of a unit vector is just any vector with a length of 1. So if I want a vector that's parallel with this one, parallel with that one, but rather having a length of root 146, 12-ish, has a length of 1, it's a really easy trick. All you do is you just take each value and divide it by the length. And if you were to redo the length calculation, this calculation with that, you would get 1. Don't bother, but you would get 1. So if you've got a vector and you can calculate its length, and you're then asked, well, what's describe a unit vector in the same direction, then that's it. And that's about that important property that vectors, if you can show that one vector is a multiple of another, by that I mean that every number has been multiplied or divided by the same thing, then they're going to be parallel, they're going to be going in the same direction. So, position vector questions, page 343, 6, 10 and 11. It's page 343 in the online version. Three, 4, 2 in the textbook version. 3, 4, 2 in the paper version. I don't know why there's a difference there. Start with just a sketch. Don't make any attempt to get it right, but you just need an O, an A and a B. And in this case you are given, Maybe we'll be sticking with my column notation wherever I can. I find it easier, this one, to answer it using my road analogy, so I can get from O to B by going along that road and then along that road. So it's 2 plus 5 and minus 7 plus 4 and 3 minus 1. So I find that easier in that case. So how do I get from O to B? Well, I can get from O to B by going up there, which is in the right direction, and across there, which is in the right direction. So that gives me my answer. There's lots of practice we can do. In 1 minute I am going to move on to the other sort of vector we meet. So just to warn you. So P to Q is just the jump, and if you're getting that wrong, then adopt my roads approach. Backwards down there, forwards up there. If you're getting it right, just by saying what do you do to get from 3 to -1, you're going down 4, that's all good. So the distance, I think it came out 25? Oh, 13. So the unit vector, oh, I'm sorry, just be aware that either form, unless it asks for one specifically, either form is acceptable. Column vector, unit vector form, either is acceptable. So the unit vector in the direction of PQ is just each of these numbers divided by 13, because 13 is the length. And whichever way you choose. I encourage you to finish 11 if you haven't already done so, but I'm afraid that we haven't got time for that now. The other sort of vector we meet then is just called a displacement vector, and a displacement vector just describes a motion from one place to another. It's not fixed in space. So a position vector is anchored at the origin. A displacement vector just describes a journey from one place to another. It's not fixed in space. And actually, this is GCSE stuff, really, isn't it? So here we've got two vectors. They're not positioned at all. This one is just any journey, wherever you're starting from, of 2, backwards 3, up 5. And this one is from any starting point, 4, backwards 2, and not up at all. And we're just asked to work out these combinations. And we can just do this with basic arithmetic. So 2 lots of A is just double that, double that, double that. 4 lots of A is 4 times that, 4 times that, 4 times that. So just see if you can answer this question. And the key part is the bit about parallel vectors.
Can you go back with me now to the maths lesson, and then I can at least just let the teacher know that you've been with me.
Oh, hello. Oh, thank you so much.
I tried.
You did a super job.
Hopefully.
Thank you very much. Gemma doesn't need it big then.
She just needs it a bit bigger, but blue.
Thank you so much.
I-
Lovely, thank you. So I write it out like this: 4 lots of A plus 1 lot of B, 2 lots of A minus 3 lots of B. Just got to be careful about the minus, so just make sure you don't lose that. And we're asked to compare it with the vector 4I minus 5K, which I find a whole lot easier to understand if I write it in that form. There's no J, so that must mean it's a 0. And then hopefully it's obvious. These two are parallel because one is a multiple of the other. each of the numbers, the x, the y, and the z numbers are multiplied by the same thing. Going this way, you're multiplying by -1/2. Going this way, you're multiplying by -2. But they are parallel because one is a multiple of the other. So look at those two questions for me. I don't know which page number I'm from. I'm confused now by my page numbers. Yeah, actually that's... I might just say, let's just do this one, and then we've got time for another example. We can add 7 to our list of independent questions if you don't get onto it. So that key phrase, because one is a multiple of the other, is all you need in terms of justifying when two vectors are parallel. Again, I know we're moving at a fairly frenetic pace, but hopefully you've got 325, which is a multiple of 6, 4, 10. You could even say what the scale factor is. It is half of 6, 4, 10, as they did there. And I say again, they are choosing to use unit notation only because you can type that in a textbook, okay? I prefer column notation just because I think it's so much easier to understand. Add question 7 to a list of questions to do. Right, so the last question. Page 342, exercise 8. So the pre-release information talks about geometric vector problems. So here we've got 2 points which together with the origin we're told make an isosceles triangle, or rather we've got to show that it makes an isosceles triangle. So there's a bit of problem solving involved here. So I'm hoping that in the time we have left you can knock up that diagram and do whatever calculations are required to show that we're dealing there with an isosceles triangle. there's 3 sides, so it may not be that these two are the equal length sides.
We like it, so who does it wrong?
So the third side of the triangle has this as its vector, and so the 3 lengths can be calculated using the triple Pythagoras thing, and we find that O to A and A to B are the same length. So it is isosceles because A to B and O to A are the same length, or we could say because that equals that. And to be honest, there's 2 very little bits of sort of new technique that we need to learn, but the rest of vectors is just using those basic skills in a variety of scenarios. Simple as that. More of this tomorrow. I like vectors.